Hi everyone, and welcome to the first video in this series on GPU compressions. So before we dive into compressions itself, let's try and build some foundation around GPUs. And the most important question to ask yourself is, why do we need GPUs in the first place? To answer that, let's think about CPUs a little bit. Most of us are aware of what CPUs do. They have been processing instructions for decades now across different systems. CPUs are ideally designed to minimize latency. What does that mean? Given a particular workload, CPUs do everything in their power to reduce the amount of time it takes to complete it. They engage in techniques like branch prediction, out-of-order execution, and so on. But CPUs start to have serious problems in two distinct applications that we're going to talk about now. So let's see the first one. Now imagine you have an 8x8 image, which is nothing but 64 pixels to handle. And for the sake of our discussion, let's have just one pixel op, right? That takes one clock cycle. For the sake of our discussion, let's say that our CPU has 64 threads. This mapping is really simple, right? You can easily assume that all of this happens in a single clock cycle because you have 64 threads and you have 64 pixels. Every thread can just literally map to every single pixel independently, and that pixel operation will be taken care of. Now, modern day frames are of the order, and there are around 2 million pixels here. Now, if you're thinking, why don't we actually give this particular workload to a CPU, right? Just see what this does. You cannot run parallelly anymore. You can just put that in 64 threads maybe, right? And you're actually seeing around 30k pixels to be operated by a single thread. So why is this a problem? This is still 30k, right? CPUs are really big enough to do it. This might be a growing problem, may not be an exact problem that you see it right away, but 30k pixels are actually going to be processed serially and not parallelly anymore. The official assumption that we made was all these 64 threads handling all the pixels independently. But now, if one pixel gets or is being processed, there are 29,999 other pixels waiting for the thread to be unlocked so that they can engage with it and they can do their operation. This is called as serial bottleneck. Now, what is the next problem that we have here is that these pixel operations are understood to be very simple, like a simple arithmetic A is equal to B plus C or something, very simple equation to solve. But that is not true in modern day graphics workloads. You will have some sort of metadata to handle, and that metadata gets stored in memory. So there will be memory traffic that you need to take care of. And with memory traffic comes memory latency as well. So this is the other problem. So what's the solution? To increase the number of threads in the system, which is what GPUs do. GPUs are designed to maximize throughput, meaning you increase the number of workload carriers and then you're getting a job done at least at a faster pace. GPUs today have thousands of threads across their thousands of cores, right? Let's say this reduces the number of pixels it has to handle per thread. And this is a huge speed up. This is the reason why we prefer having a GPU handle this type of graphics workload. Now, another problem that GPUs don't solely handle, and that is about memory traffic. And this is where you pair GPUs with HBMs. HBMs are short for high bandwidth memories. They are actually designed to cater thousands of these threads, incoming threads, with different types of memory requests at the same time. Now you might wonder, why can't we actually pair a CPU with an HBM, right? I might still be well off and not have memory latency. Well, that is not true, because even if you pair it with a CPU, you're not actually using the bandwidth. You don't have enough threads to. So this actually takes care of our first problem, that is a graphics workload. So now let's talk about the second one. And as of 2026, we call this AI. At its core, you have a neural network being running. There's a single node that connects to 3 nodes, and there are more such layers and so on, right? Fancy stuff. So if it's just a simple system that has just 4 nodes, you can easily model this in a CPU. But modern day systems have scaled to such a level that there are billions of such nodes, billions of weights, right? Billions of inputs again, right? And this is just scaled to something that is not even practical to be handled by a single CPU core. This is where stuff gets a lot parallel, and GPUs are again here for your rescue. And this is why you see everybody scrambling to get their hands at a GPU, right? And even modern day ASICs that are being designed to, handle such massively parallel workloads. So now we are talking all about GPUs and, why GPUs are better and everything. So why do we even need CPUs anymore, right? Because GPUs are doing everything. Well, if you actually give a CPU this type of problem, you give that to a CPU handles this differently. It doesn't handle this always serially. It might look at some things where it needs to, do something out of order so that other instructions don't have to wait. If you give the same task to a GPU, at a massive scale, they will fail, because GPUs were never designed to actually think. GPUs were designed to execute. That is not as smart as a CPU would be. This is the reason why you would see this play out today as well in modern day, where we talk about agentic AI, where one particular agent is deploying different other agents, and it has to take care of reading outputs or moving traffic from one agent to another and whatnot. So CPUs are heavily dependent on in terms of orchestration. So whatever all this agentic decision making happens, it happens on a CPU, whereas all the model computation and the true execution of that code happens on a GPU. So this is the foundation. And with that, I will see you on the next one. Thank you.